With that in mind, I always start with two pieces of advice. These are very good pieces of advice if you're going to take any exam, but particularly for math exams, which is number one, do problems. Because the more problems you do, the more you sort of start to say, oh, I recognize ideas and patterns and what to do, and it really helps. So the more problems that you do before the exam, the problems that you see on the exam won't seem so bad. And there's no big, huge surprises. Many of the problems are very similar to quiz problems, and ones that aren't very different. So if you're prepared, you should not panic. Second thing, take care of your health. We know exams are stressful, so take some time to make sure you're okay. Go out, it's beautiful weather for this time of year, take a walk, eat some good food, get plenty to drink, like water when I say drink. And if you need to scream into your pillow, that's okay. We make no judgments. Just take care of your health. All right, so we have 12 problems. I think it's 12. So lots of fun ahead for us. Start with number one. Find an implicit solution to the following. So we have 1 minus cosine 2y, y prime, minus 8x cubed cosine squared y equals 0. Now, as we're going through here, one of the things we want to develop is to say, well, what kind of problem do I see? What is this? And there's a few clues here. So in this one, it's trying to hint at something. You see the word implicit. That's a kind of a clue that something might happen. But also the way that this problem has been written is kind of a clue. Now, what problems do we tend to see written in this format? Any thoughts? What tends to look like this? Meditation, good. So I will say, this sort of feels like exact. Now, why do I say it feels like exact? So exact tends to have the form something y prime plus something equals 0, or something dy plus something dx equals 0. So when you see things like that, you probably should start thinking, I suspect it might be exact. So let's see if it is. How does one figure out if something is exact? Well, I like to do it by, let me solve it, and if I get stuck, then I know it's not exact. It's a good strategy. Okay, so really, if this were exact, I'd be thinking of this as 1 minus cosine 2y dy. So I'm going to think of this as y prime as dy over dx. So I'm going to multiply through by dx. Minus 8x cubed cosine squared y dx equals 0. So this would be that kind of spirit. And the idea says exact, says, okay, this should be the derivative with respect to y. Here should be the derivative with respect to x. So we integrate 1 minus cosine 2y dy. And all right, that says y is our variable, and treat any x's like constants. Okay, so if we did that, integral of 1 with respect to y is y. Integral of cosine, positive sign, there's a minus already, so minus sine of 2y, and then divide by a half. And then you'd say, well, anything that's a constant with respect to y, so a constant function of x. And then we say, okay, now integrate this other part, this minus 8x cubed cosine squared y dx, right, with respect to x. Well, all right, the cosine squared y, here, it's a constant. Cool. So I don't have to worry about this x cubed. Integral of x cubed is x to the fourth, because you add 1, and then you divide by 4. And, well, okay, so we have this minus 8 times 1/4 x to the fourth cosine squared y plus something of y. Okay, so now I stop and I ask, am I going to succeed? Is this exact, or have they tricked us? All right, so question, is this exact, or have we been tricked? We have been tricked. It's not exact. Now, why not? Well, you see how this part has both x and y? There should have been something with x and y that matches it up here. So, no match for the xy part. That equals not exact. Okay, so we fell for their trap. All right. Now, how do we proceed? And you might say, why did you do this if you knew it wasn't exact? Well, because I do want to show you that sometimes you try things and it doesn't work. And what happens? It doesn't work. And then you do something else. And so if you saw at this point, it's like, oh, this is going to fail. Should you try to keep making it succeed? No, because you're not going to get any points. And so be careful. It may not always work the first time. I will say, in case you're getting nervous, like, oh my gosh, the test is not like that. The test is much more on the nose. But, okay, all right. So we try something else. So it's not exact. And you might think, why write it that way? Well, I will say that there are such things as mean test writers. And they're like, we know how you think. And the reason we know how you think is we programmed you. And so we're going to take advantage of that programming and make it look like one thing when it's really another. So take your time. Okay, so if it's not exact, that leaves us with sort of two other options. Because when it comes to solving differential equations, first order differential equations, you got three tools. Exact is one, linear first order is the other, separable is the third. Okay, so we've ruled out exact. All right, so let's come back. So let's now say, okay, could it be linear first order? And why not? Well, no. Hopeless. Because linear first order says you should have a y prime and a y, and that's it. Any function of y, forget it. It's not linear first order. Okay, so that makes our list very short. We're down to one thing. And so what are we down to? We're down to separable. Okay, cool. So, separable. So that's the real way to approach this problem. Okay, so how do we make it separable? Well, the idea of separable is we want to separate. So we start moving things around. Well, let's move this 8x cubed cosine squared y to the other side. So we have 1 minus cosine 2y y prime equals 8x cubed cosine squared y. Okay. At some point, we should look at this 1 minus cosine 2y versus this cosine squared y. The thing is, when we deal with trigonometric functions, we want the insides to be looking the same. So one of these has a y on the inside, one has a 2y on the inside. That's not going to work. So, is there a way to rewrite? And we start looking at things like, maybe there's a formula sheet, because there is. And we start looking and saying, well, does anything show up? Now, there are things that show up. For instance, sine squared y is 1/2 1 minus cosine 2y. That you can derive from your formula sheet. So, that says we can replace this. Well, be careful of the half. So this would become 2 sine squared of y prime, again, just anticipating separation. When I'm thinking separation, I like to write as dy over dx so I can move things around easier, equals 8x cubed cosine squared y. All right, this is feeling better. Now, we'll move things around. So we'll move the cosine squared across by dividing. We'll move the 2 by dividing. We'll move the dx by multiplying. So there's a lot of little operations happening here, but nothing individually too surprising. Sine squared divided by cosine squared, also known as tangent squared. Good. And then the dy. On the other side, 8 divided by 2, well, that's 4. X cubed stays there, and a dx. Okay, so good news is we've now separated. So we're pretty happy here. So this does indeed verify to us that this is a separable differential equation. Whew, good. And not only do we know it's separable, we've actually done the first step, which is we've separated. Now we go into the next step, which is integrate. All right. One of these doesn't look too bad. The integral of 4x cubed doesn't look too bad. So we actually even did it over there. That's x to the 4th plus c. Because, you'd add 1 to the exponent, that'd give you x to the power 4. You divide by the exponent, and the 4's cancel. Do we have the integral of tangent squared y on our equation sheet, perhaps? No, we don't. But what do we have on our equation sheet? We have the integral of secant squared y. Well, I think it's secant squared u, but let's pretend like it's a y. Do we remember what the integral of secant squared is? Tangent. Now the question is, can you make a tangent squared look like a secant squared? So tangent squared plus 1 equals secant squared. Now how would we possibly know that? It's on the formula sheet. Like, isn't that cool? Now here's, by the way, a professional piece of advice. It turns out we spend a lot of money. You can detach the formula sheet. So you don't have to keep turning your test back and forth. You can take the back page off. We paid extra for that feature. And so, have it handy. Don't be like, I'm never going to look at it because I'm just super confident. Like, no. This is not the time to just be like bold. Don't go in there and be like, aha, I don't need no formula sheet. Okay, so tangent squared becomes secant squared minus 1. And then the integral of secant squared is tangent of y. And the integral of minus 1 is y, because we're integrating with respect to y. So we have tangent of y minus y equals x to the 4th plus c. And what happens next? We're done. We don't have any initial conditions. And so we're good to go. Now, I will say, make a comment here. When you see the word implicit, you should always say, most likely it's exact. That's probably about 80% of the time. The other 20% of the time, it's separable. Linear first order, we never ask for implicit, because linear first order, you're guaranteed to be able to solve for y. And so when you see implicit, you basically know you're looking for, most of the time it's exact. A couple of rare instances, it'll be separable. Okay, good. Well, other than the misdirect, hopefully not too bad. Any questions? Don't worry, no more misdirects. Everything will be super obvious. Maybe. Number 2. Find y of x, given that y, when you plug in e, is 2. And we have x log x y prime minus 2y is log of x to the power 4. Now keep in mind, this 4th power is outside of the log, not inside of the log. Know your rules of logs and make sure you follow them. And so it's not like, bring the 4 down. No. That's not what's happening here. Okay, so thinking about our 3 types of first order differential equations. Remember, We talked separable, linear first order, exact. Which one are we in? Linear first order. What gives it away? When you see a single y prime and a single y. If you see there's a y prime and a y and nothing else with y, linear first order. Okay, so we know it's linear first order. So cool. Now that we know what it is, we need a plan. And our plan, our big idea, when we see linear first order, is, well, integrating factor. Some classes use rho, some classes use mu, but the point is you're looking for that integrating factor. Okay, so how do you find it? So first step is you take a look and you say, hey, what's in front of the y prime? Well, it's x log x. What do we want in front of the y prime? We want it to be 1. So we say, no problem. We have the power of division. So we're going to take everything and divide by x log x. All right. So doing that, what do we have? We'll have y prime minus 2 over x log x is equal to log of x to the 4th over x log x. We could even simplify this. Notice that there's 4 log x's upstairs, there's 1 downstairs. So this is log of x cubed over x. Okay. And I forgot to write down my y. I am so sorry about that. That was super important. That's good. That's why we double check. Copying errors are one of the biggest sources of mistakes. And so it doesn't hurt to just make sure, did I copy something down correctly? All right. Well, good. Now, what happens next? Well, the next thing is now that we have a 1 in front of our y prime, we're going to look at this part attached to the y term. This minus 2 over x log x. And what we're going to do is we're going to say, okay, we're going to have our integrating factor. Do you want me to use mu or rho? Mu? All right, we see a lot of Chris Lee students are here today. I like Chris Lee. I think he's one of the few professors I want to go one-on-one when it comes to a teaching battle. We haven't had the chance yet, but someday, there's always the dream. Someday. Okay, so we're going to integrate what's in front of the y, and then after we integrate, we're going to take e to that, whatever that is. Okay, so now we're faced with the interesting situation. What is the integral? The minus 2 comes out. 1 over x log x dx. It's not on the formula sheet, unfortunately. Oh, someone has an idea.
We can do substitution.
Yes. Yeah, look for substitution. If something's not on the formula sheet, look for substitution. We're not going exotic here. And usually it's not going to be something crazy. When I say usually, like during an exam, u is log x du, 1 over x dx. Oh, ho, 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 we have a 1 over x dx. Nice. So this becomes minus 2. Then the log x is downstairs, 1 over u, and dx over x is du. Now the integral of 1 over u du, is that on our formula sheet? Yes. It's the log. And then we say, okay, put back what u is. So this is minus 2 log x. Log x. Yep. Cool. And now you might be wondering, like, oh my gosh, is this going to come out to something we can integrate? Looking ahead, don't worry, have faith. Problems have been carefully chosen to work out. Surprisingly nice. Okay, so when I'm doing the integrating factor, what can I do with this constant? I can't ignore it. So, doing the integral gets us minus 2 log x. Now we're going to test our powers of logs. And so this is why you really need to know your logs rules, because logs show up when you talk about these linear first order problems. So you want to be comfortable with them. Where does the -2 go? Comes in as an exponent. So this is the same as e to the natural log of x to the -2. Okay, so I move the -2 in. Because in particular, I want to have e to the log of stuff. Because e to the log of stuff is stuff. It works out really nicely. So our integrating factor is log of x to the -2, or 1 over log of x squared. All right? Good. Oh, what a workout. It feels like we should be done with this problem. We're halfway. But this is an important half. Okay. So any questions on this step? Because this is an important step. And if you don't make it through this step, what comes next is going to be like, what?
Where does the outside log go?
This log here?
Yes.
So the outside log, because the exponential function log functions are inverse functions of each other. And so when you do a function followed by its inverse or vice versa, they're like, okay, move it here, then move it back. And so what happens is you're basically back to what was on the inside. So that's why we like to write things as e to the log of stuff, because e and log undo each other.
So the ln and the cancel.
Well, they undo each other. Yeah. You can think of it as they cancel, if that helps. All right. Now, what do you do with this integrating factor? Well, the answer is you multiply everything. Oops, sorry. Come down to here. This part. You multiply everything by 1 over log x squared. Now, you can save yourself a step. Is it okay if I save myself a step, or do you want me to do it in like slow motion? Slow motion? Okay. So, I'm going to multiply everything by log of x, 1 over log of x squared. So 1 over log of x squared y prime minus 2 over x log of x cubed y is equal to, and here it's going to be log of x over x. Now, the step I can save is that this left-hand side, by design, it's guaranteed to be nice. It's super duper guaranteed to be nice. And why do I say that? Well, it's always going to be, and if it's not, mistakes were made, the derivative of your integrating factor, 1 over log x squared, times y. The whole punchline, the whole reason why we're doing all of this is because that left-hand side becomes nice. So oftentimes when I'm doing a test, I'll skip this intermediate step and go right to here. And I say, I know it's the derivative of the integrating factor times y. And then I remember I have to take the right-hand side and multiply through by the integrating factor. Okay, now the next step. We're going to integrate. We're going to integrate both sides with respect to x. The cool thing is, it's really easy to integrate a derivative. The way you integrate a derivative is, it's just what you started with. 1 over log x squared y. Okay. How does one integrate log x over x? Any thoughts? Yeah, we're going to do substitution again. It's a substitution so nice, we're using it twice. So if u is log x, du is 1 over x dx. So then this becomes the integral of u du. Well, what's the integral of u du? U squared over 2. So we say, all right, so putting back what u is, 1/2 log of x squared plus some constant. Okay, now we do need a constant at this stage. So 1/2 log of x squared plus some constant c. Okay, now let's go ahead and solve for y, because we have to find y. See how it says we have to find y? So we're going to do that. So multiplying through by log squared, we get that y is equal to 1/2 natural log of x squared plus, squared times natural log of x squared makes it natural log of x to the 4th, plus some constant c, natural log of x squared. All right, are we done? No. Are we close? Yes. So what's left? Yeah. Always check. What kind of problem do I have? Is it one that gave me an initial condition, or is it one that didn't? Am I looking for a general form, or am I looking for a particular solution? So here, we're looking for a particular solution, so we plug in. So we're going to plug in x equals e and y equals 2. So we say that 2 is equal to 1/2 log of e to the 4th plus c log of e squared. Now, what's another name for log of e? It's 1. The natural log of e is 1. So it's 1/2 plus c. So what does that tell us about c? 3/2. So we end up with saying that our final answer, 1/2 natural log of x to the 4th power plus 3/2 natural log of x squared. And since we're out of paper, that must be the answer. All right, good. Any questions on this one? Then we will move on to number 3. Find an implicit solution. Oh, no, after number 1, it's like, okay, Steve, I don't trust you that much. But okay, find an implicit solution. We have 3x squared cosine y minus secant squared x dx minus x cubed sine y minus 6e to the 2y dy equals 0. Okay, so when you see it like this, what should be your first instinct? Exact. Don't let past things like, even though you see that 1% of the time when it's not, we still go with the 99% that it is. Okay, so when we're doing exact, now I'll comment here that there is a test for exactness that sometimes people say, well, test for exactness first. I find it's just so much easier to just solve it. And if you get stuck, then you know it's not exact. Okay, so solving, we're going to integrate the first part with respect to x. We're going to integrate the second part with respect to y. So it's kind of nice when you see it in this form. Now, if it's not in this form, so for example, if it's a y prime, write y prime as dy over dx and multiply through. So integral, we have 3x squared cosine y minus secant squared x dx. How do you treat the cosine y when we're integrating with respect to x? Constant. So it's a constant, 3x squared. Well, the integral of 3x squared is x cubed. So we get x cubed cosine y. The integral of secant squared we've talked about already. That's tangent. And then add in some unknown function. Okay, now the second integral. Okay, x cubed sine y minus 6e to the 2y dy. Okay, now we're integrating with respect to y. So how are we going to treat this x cubed? As a constant. What's the integral of sine? Integral of sine? Negative cosine, right? Minus x cubed cosine y. Integral of 6e to the 2y? With respect to y? Negative 3 e to the 2i. So it's e to the 2i divided by 2 plus some function of x. Now, are we matching with the xy terms? No, we're not. But what do you notice I did? There was a minus sign here. We didn't copy that minus sign. Whoops. So now we'll fix that. That's how important those minus signs are. So if you see a minus sign outside of parentheses, don't forget it. All right. I feel like I'm not trying to scare you. I just want you to say, I've made mistakes in the past. I'm sharing you all the mistakes I've made. I once had a teacher hold up my homework assignment, and he said to the class, look, Steve wrote down 1 plus 1 equals 1. He makes mistakes. So, you know, I make mistakes. It's true. All right. I just want to show you some of my mistakes. Okay, now that we fixed our sign, okay, are we exact? What's the test for exact here? Well, you look at the parts which have both x and y, and you ask, do these match? Do they match? Yes. So these match. So exact. Okay, so now we know we're exact. And in fact, we're most of the way done. Okay, so what do we do to finish up? Well, we grab the parts where they match. That's the x cubed cosine y. And then we say, okay, we grab the part with just the x terms. So that's the minus tangent of x. And then we grab the parts with just the y terms. That's the 3e to the 2y. And then we take all of that and set it equal to 0. Oh, sorry, not equal to 0, equal to a constant. Arbitrary constant. Okay, so it's the overlap, parts just with x, parts just with y equals constant. So that's the general form for solutions. Are we done here? Yes. So we're done. Now, let's talk about two things. Sometimes it will say, indicate why you know it's exact. So there's two ways to indicate how you know it's exact. One way is to check that these match. So that's method number one. Method number two is you take the derivative of what's in front of the dx term with respect to y, take the derivative of what's in front of the dy term with respect to x, and ask if they agree. That works, but it doesn't help you get to an answer, which is why I don't use that approach. So that was comment number one. So just know how to say, I know it's exact because of this. The other thing is, they might give you initial conditions. Now, when they give you initial conditions, it comes in the form of a point. You know, first coordinate, second coordinate. How do you use your initial conditions to solve for your constant? What do? Yeah, you plug the point into the left-hand side. Whatever number comes out, that's C. So exact problems are fun. So it's one of those things we hope for on exams. All right, questions? Okay, good. I haven't been keeping up with I need to go faster. I'll go faster. Number 4. Carry out the indicated substitutions to rewrite the differential equation, which are finding functions y of x. So we're solving for y as a function of x. You do not need to solve the resulting differential equation. Oh, thank goodness. Okay, so here we're just practicing substitutions. All right, most of the time substitutions fall into 3 categories: Bernoulli, homogeneous, and we will tell you. So those are the 3 categories. Now, the first one, this is actually a Bernoulli type substitution, and when we talk about Bernoulli, it's about something like you substitute u as y to a power. All right, so let's go through. We just need to do the substitution. So we're almost like putting on our Calc 1 hats. It's very similar to substitution and integration. All right, so how do we do it? Well, what I like to do, so let's start with part A. And we have, we're substituting u equals square root of y, or y to the 1/2. Now there's sort of two ways you can approach this. Now what I like to do is I just say, let me take the derivative. So u prime, and I say, okay, take the derivative of both sides. That's 1/2 y to the minus 1/2 y prime. So I took the derivative of both sides, like you would in substitution. And so I say to myself, okay, the 1/2 I can move around. So we could say 2 u prime is 1 over square root of y, y prime. So what I'm looking for is, can I rewrite to put a square root of y downstairs here? So I want to put a square root of y downstairs. I'll say, yeah, that's easy. If I want to put a square root of y, I'll just put a square root of y. So I'm going to multiply everything by 1 over square root of y. So 1 over square root of y, y prime. Here, the square root of y's cancel. Then over here we get 10x, and this will become y divided by square root of y is square root of y. So I multiplied through by 1 over square root of y. And now it's pretty straightforward. 1 over square root of y, y prime becomes 2u prime. 2 cosine x becomes 2 cosine x. We're not touching it. We're only playing around with the y terms. The 10x is 10x, and the square root of y is u. So there's part A. Okay? There was a second thing I said you could do, and I'll point it out here. The other thing you could have done is you could have said, hey, you know, I could have said that y equals u squared. If you square both sides, so then y prime would be 2u u prime. And then you would just make the substitution. So you'd have 2u u prime equals 2 cosine of x u, and then plus our 10x u squared, and then just divide through by u. Both work. So just use whatever works for you. Okay, good, good. I will say, for the purposes of this exam, oops, sorry, I went off the screen there. Don't stress too much about having to find the substitutions. We will help you with that part. But know how to do the substitutions. All right, so part B. Now part B, y over x, classic, this is homogeneous. But not the homogeneous we'll talk about later. This is the other homogeneous. We ran out of terms, so we had to start recycling. All right, so homogeneous substitutions are basically everything's looking like y over x. Now you might say, well, wait, it looks like y over x? Well, it does. You have to play around with things. So let's just move things around so it feels like y over x. So notice I have a y, there's an x. So I can write this as y over x, e to the y over x, y prime, log of y minus log x. When I'm subtracting logs, what does that become? Becomes division, y over x. So this problem is really like, yeah, everything looks like y over x. So no wonder they want us to make this substitution. So we haven't substituted, all we've done is rewrite. And I don't want to make it sound like all we've done is rewrite. Rewriting is really cool. It gets you surprisingly far. Now, when it comes to doing the substitution of y over x, I would always start by solving for y, because it just is so much cleaner. I think part of it is just I've made so many mistakes with fractions over the years. I'm somewhat fraction averse. So I avoid fractions as much as I can. So I say, okay, so instead of y over x equals u, we'll say y equals x times u. So then what is y prime? Well, what rule do you need to take that derivative? Product rule. All right, so derivative of the first, 1 times the second, u, plus the first, x, times the derivative of the second, u prime. And now we go through term by term. Okay, y over x, u. E to the y over x, e to the u. Y prime, u plus x u prime. Log y over x, log u. Now, we've succeeded with our substitution if there are no more y's. So we're substituting for the y's. Are there no more y's? Yes. So we're done. We didn't have to clean it up or solve it. We just had to substitute. So there we go. All right, so that was B. All right. Getting us to C. Sometimes you write a problem and then you realize in retrospect it's your favorite problem that you've written in a long time. That's how I feel about part C. After I wrote part C, I was like, I feel terrible I couldn't put this on an exam because this is such a cool problem. I hope you'll feel that way too. All right, so let's find out. So y prime equals secant of y, x plus sine y squared. Okay, I don't know why I'm copying again, but I did. All right. We're making a kind of a strange substitution, x plus sine y, but we're allowed to make any substitution we want. And it kind of isn't the craziest thing, because if you think about what substitution is, think about substitution with integration. It's an inside job. So we're looking for a function on the inside, and we see this x plus sine y squared. All right, so we say, okay, what's u prime? Well, what's the derivative of x plus sine y? Derivative of x is 1. Sine y, cosine. And then chain rule, y prime. Okay, so we want to get a cosine y, y prime plus 1. Secant y. What's secant also known as? 1 over cosine. So, multiply both sides by cosine, you get cosine of y, y prime, equals x plus sine of y squared. Okay, so we're pretty close. What are we missing? What's not there yet? We're missing the 1. Where do we get the 1 from? We just put it in. You're allowed to put it in. You just put it into both sides. As long as you do it to both sides, you're good. You're allowed to manipulate the equation as long as it's equivalent to what you started with. All right, so 1 plus cosine y, y prime, also known as u prime. And then this other side becomes u squared plus 1. So that our new differential equation is u prime equals u squared plus 1. Now you're probably thinking like, why would Steve fall in love with this problem? Do you really have to ask? This becomes du over u squared plus 1 equals dx. It's separable, which becomes arctangent. Oh, what a problem. And now I can't put it on the test. Oh. No, I can't. But, you know, I'll get to teach differential equations sometime in the future. So maybe by then, people's memories will be faded out. They'll stop watching the old reviews. All right, that leaves us with one more. And we don't have a lot of space, but we'll see if we can fit it in. So, y double prime plus 6y y prime minus e to the y prime equals 0. And we're going to substitute u equals y prime. Now this one is the weird one. This is the one that almost everybody says that's not right. And then we keep telling them that it is, and then they give up and say, okay, fine, I'll just go. Why is it weird? Well, because it's not u as a function of x, it's u as a function of y. Notice how all these others, we were very clear, u of x, u of x, u of x. Here this says u of y. Now, why is this going to be strange? Well, when we talk about y prime, this is where the notation gets dangerous. Y prime means the derivative of y with respect to x. If I want to take a derivative here, the next derivative I should take is again with respect to x. So if I take the derivative of both sides, so the derivative of u equals y prime. So I'm taking the derivative of both sides with respect to x. The right-hand side, that's pretty easy. It's just the next derivative. The left-hand side is the one where you have to let me think about that one. Okay, so what is the derivative of the left-hand side? Now I know I've been making it very dramatic here. So what's the derivative turn out to be? Well, it's u prime. Now that's if u prime were a function of x. Is it a function of x? See, I've left a suspicious gap here. It's a function of y. So what do you have to apply? The chain rule, which is y prime, derivative of the inside. But what is y prime also known as? It's also known as u. So this is u prime times u is y double prime. So this is the weird one. But now that we know it's the weird one, we know to anticipate. Okay, so what happens? Well, we're not going to replace any of the y terms. We're going to replace the y double prime and the y prime terms. So y double prime becomes u prime times u. The 6y y prime, well, the y term stays as is. The y prime becomes u. E to the y prime, e to the u. And at this point, we're done. We've made the substitution. So we've carried out the substitution. So this is the one that's a little strange. But once you see it, and okay, it works. And the nice thing is, we don't have to solve. Our favorite sentence. Okay, good. So, any questions?
For the u equals x plus sine y.
Right, x plus sine y.
How does u prime equal 1 plus cosine y prime?
Well, we're taking the derivative, when we talk about u prime here, so whenever we're taking derivatives, we always think of derivatives with respect to x. So the derivative of u is u prime. Derivative of x with respect to x is 1. Derivative of sine of y, because we're taking derivative with respect to x, you have to use the chain rule. So derivative of the outside, cosine y times derivative of the inside, y prime. So that's what's happening. Okay, number 5. Oh, words. So many words. Why do there have to be so many words? All right. A large tank. Oh, tank problem, mixing problem. All right, we should draw a picture here. Let's draw ourselves a tank. So here we go. And we'll know it's a tank because we'll write the word tank on it. There we go. Hey, tank. A large tank initially has 10 gallons of pure water. Okay, so let's make a note here. Initially, 10 gallons. And pure water. Now that's probably important. We'll make a note of that and come back to that. At time t equals 0, a valve opens and salt water, which we often call brine, comes into the tank. Okay, so there's something coming in. And it's coming into the tank. There's 2 gallons per minute. All right. And a concentration of salt, S ounces per gallon. But it doesn't tell us what S is. All right, S ounces per gallon. Okay. Simultaneously, a valve opens and it drains well-mixed fluid from the tank at 1 gallon per minute. Okay, so down here, this is 1 gallon per minute. All right, now what are we told? Given that after 20 minutes there is exactly 80 ounces of salt in the tank, then determine how much salt is in the tank after 40 minutes. Okay, so let's give things a name. Names are good. We should name things. So let's let x of t, and this is our function we care about. This is the amount of salt in the tank at time t. Okay, so what are some things that we know or want to find? So we are told that after 20 minutes there are 80 ounces of salt. Okay, because that's what it says. After 20 minutes there's 80 ounces. Now there's another thing. Remember we mentioned pure water. Pure, no salt. So plug in 0, we have 0, right? So at time 0 we have 0. Okay, so the question becomes, well, what is there at 40? Okay, so that's what we're after. Now you might say, well, we have 80 ounces that came in the first 20 minutes. We're always having the same amount of salt coming in, so maybe 160. All right, well, okay, maybe it's 160. Maybe not. Now, 160 is going to be ballpark, we think. So if our final answer is like 1,000,000 ounces of salt, we should check. Okay, so how do we begin? Well, tank mixing problem, right? So let's set up our differential equation. Now, all tank mixing problems have the same kind of differential equation. So we're saying, how does the salt change? Well, there's only two ways salt can change. Something came in or something came out. It's not like there's, we were just sitting around and then all of a sudden, salt. No. There had to be a place where it came from or that it went to. So the change in salt in minus out. So we have our in and our out. Now our in, that's pretty easy, right? Because we know the rate at which the fluid's coming in. We know the concentration. Well, we don't actually know the concentration, but we can pretend like we know. So we would multiply these together and have 2s. All right, be careful here. That's an s, not a 5. This is one of the dangers of working with the letter s. Minus. Okay, how about out? Now this is the out. That's the part where oftentimes you have to be careful. Let's look at our tank. What can we say about the, if you will, like the water level, the level of the fluid? Is it going up? Is it staying the same? Is it going down? How do we know? Well, we know how much there is initially. There's 10 gallons. And we look at the inflow versus the outflow. You'll see that 2 is bigger than 1. And so what's happening is when you look at the difference to subtract 1, that says we're gaining 1 gallon per minute. And so we can say that our water level is going up. And so in particular, the fluid level, well, that's going to be a function, and it's going to be 10 plus t. So this is how much brine there is, or water plus salt. Okay. Now, how do we figure out our out? So the out, well, think about what was happening here. You had a flow rate and a concentration. All right, so let's do the same thing. Flow rate is 1. So 1, what's our concentration? Well, it's the total amount of salt. That's x, divided by, total amount of fluid. That's 10 plus t. All right, right? Concentration, salt over fluid, life is good. Good. Well, great. So now we have a linear first order. We know how to do those. We've done those before. And so we'll do it again. All right, so let's start by rearranging. So we have that x prime plus 1 over t plus 10 x equals 2s. Okay, so we'll need our integrating factor, so we'll do some computations on the side. So we're going to do e to the integral 1 over t plus 10, And if we do that, that's e to the natural log of t plus 10. Remember, we don't need to worry about constants when we're doing integrating factors, which means our integrating factor is t plus 10. So we're going to multiply everything through by t plus 10. And so that would be, well, t plus 10 x prime plus x equals 2s t plus 10. All right, good, good. And by the design of our integrating factors, this left-hand side is very nice. So this is the derivative by design, integrating factor, t plus 10 times our function x. Okay, so we're almost there. Now, what are we going to do? Well, we're going to integrate. And so we integrate both sides. And when we integrate, well, it's not so bad. What's going to happen? We're going to get on the left-hand side, it's our integrating factor times x. Over here, well, it'll become s times t plus 10 squared plus c. Okay, cool. Well, now we're going to start using our two pieces of information, namely what happens at time 0 and what happens at time 20. That'll let us solve for our two unknowns. So we actually have two unknowns at this point, s and c. One of them comes from solving the differential equation c. One of them comes from the setup of our differential equation from our model. Well, okay, so we got to solve. So let's plug in. So let's say we know x of 0. Well, first off, let's actually solve. What is x of t? So that's s times t plus 10 squared plus c over t plus 10. Okay, x of 0 is 0. And when we plug that in, we're going to get s, 0 plus 10. Well, that's 100s. And then we're going to get plus c over 0 plus 10 is, well, 10. Okay, you can imagine multiply the 10 through. And what do we see? Well, we see that c should equal minus 100s. All right, well, does that help us? Well, yeah, it does. Now, let's actually do something here. Let's see, there's something really cool here. So imagine that you squared this. So this is s t squared plus 2t plus, sorry, not 2, 20t, plus 100. And then c is minus 100s all over our t plus 10 downstairs. All right, now see, distribute 100s minus 100s cancels. And so the punchline here is that we now have s, and then t squared plus 20t becomes t times t plus 20 over t plus 10. All right, good. Now that's just from our initial conditions. And that's already something which is very reasonable to work with. Almost solvable, right? Well, we hope. All right, so next up, when we put in t equals 20, we should get out 80. So 80, that's the same thing as when we plug in 20 in for our time. So that's s times 20 times 40, right? 20 plus 20, and divide by 30. Okay. Well, if you move things around, we can do a couple things. Notice that we can cancel some factors of 10s. 20 times 4 is 80, so that can cancel. And what's left? Well, that says that 1 is s over 3. Well, that tells us that s is 3. Aha! So our concentration of what was coming into the tank, it had 3 ounces per gallon. And so now we update one more time. Say, okay, so that tells us that x of t is equal to 3t, t plus 20, divided by t plus 10. Okay, now we're almost there. The only thing left is plug in 40. Okay, so here we go. Well, we'll do it here. We might have enough space. X of 40. Well, that's 3 times 40, right? Because t is 40. 40 plus 20, 60. And then 40 plus 10 is 50. All right. Well, again, we can cancel a factor of 10. 5 goes into 40, 8. So we have 3 times 8 times 6. So that's 3 times 8 times 6. If you like, that's 24 times 6. That's 24 times 6, that's 120. And then plus 24 makes 144. And so, what do we have? Well, the answer is 144. And we'll throw in some units just to be extra careful. So we have 144 ounces. That's it. There we go. There we go. Now, is that reasonable? Well, notice that we started, after 20 minutes, we had 80. And so we said roughly we should hope for something close to 160. And 144 is not that far off from 160. You might wonder, well, wait, why is it below 160? Well, initially, we really didn't have much salt leaving because it was very pure water at the start. And so what happened is as our water got saltier, we actually had more salt leaving than we did before, which is why we would expect there to be a little bit less salt added overall between 20 and 40 as compared to between 0 and 20. But okay, moral is it's a reasonable answer. And it's an answer, right? We love answers. Answers are great. All right. Whew. All right. Good. On to the next problem. Okay, number 6. There we go. Well, let's get back on track with something where we'll succeed. So, given the graph of f of y shown below, find and classify all critical points between -4 and +4. You'll see there's a grid here. So this is -4. This is +4. So there's our nice grid that's been drawn for us. All right. For the differential equation, y prime equals y minus f of y. So this is the autonomous differential equations, the find and classify type of differential equation. Okay, so how does one proceed in such a thing? Well, you sort of channel your inner Calc 1 student, think about, okay, first derivative test. So we are interested in understanding when y prime, we have this generic equation, y prime equals y minus fy. When y prime is greater than 0, this says that the y values are increasing. And when y prime is less than 0, this says that the y values are decreasing. So we're going up, we're going down. When y prime equals 0, these are what we call the critical points. Now, you'll notice it's not y times f of y, it's y minus f of y. So what are we interested in? So let's start with the y prime equals 0. Well, that tells us we want 0 to be y minus f of y, or f of y equals y. So in terms of the picture, what are we looking for? We have the f of y shown here. So this is f of y. We don't have y shown, so we're going to have to sketch it. So we're going to have to use all our skills to draw in the line y. So the good news is, because there's a grid, that's pretty easy to draw. So we have y, and we have f of y. Okay. So when we're looking for critical points, we're looking for where these touch, where y matches with f of y. So it's not where f of y crosses the axis. There's 3 critical points. So we have one at -3, at -1, and at +2. So those are the critical points. We've found the critical points, but now we need to classify. Okay, so let's talk about what's going on. Y prime greater than 0. Well, that says y minus f of y is greater than 0, or y is greater than f of y. So, where y prime is greater than 0, what should be on the top? the y curve or the f of y curve? So if we want y prime to be greater than 0, the one on the top is the y. So where is the y curve on top? In this stretch. So the y curve is on top in this region, which means that y prime is greater than 0. Y prime greater than 0, are we going to the right or to the left? So where am I, which direction is increasing? To the right or to the left? To the right. To the right, the numbers are getting bigger. We're increasing. So that says we would be going to the right, because y is above f of y. So y minus f of y is positive. If we want y prime to be less than 0, well, that says that y minus f of y is less than 0, or y is less than f of y. So then here I want the curve y to be below f of y. That's in the ends. So y is below f of y. Y is below f of y. So we're decreasing in which direction? To the left. So I always draw this nice graph just to help me capture, okay, what's going on. So we have our 3 critical points. -3, -1, 2. -3, we're moving away from -3. What kind do we have? Remember that our choices are stable, unstable, semi-stable. Moving away means unstable. Okay, -1, where both sides have the same behavior. What's that? Semi-stable. In 2, we're moving in. What's that? Stable. And seen. We're done. All right, good. Good. Any questions on that one? All right.
How did you get that y line?
How do I get the line y? Well, essentially I used the grid. So you'll see that there's a grid in place here. And so I used the grid to draw it. It's a 45-degree line. So I used advantage of the grid. All right. Number 7. The size of a cluster of mushrooms measured in pounds after time t measured in days, okay, lots of words there, follows a logistic model. Okay, we see logistic model, we automatically know logistic model. We say, hey, that means that p prime is some constant k times p times m minus p. We just automatically know that. Now the nice thing about this particular equation, well, what is the nice thing about this particular equation? It shows up on the formula sheet. And not only does it show up on the formula sheet, it says, hey, if this is your differential equation, so you should say isologistic, I automatically know it's this equation. And moreover, I know that P of t looks like mp0 divide by p0 plus m minus p0 e to the minus kmt. Again, this is on the formula sheet. So as soon as you see logistic models, like, I'm going to the formula sheet, I'm copying this down because I'm going to use it. Okay, cool. Then we can keep reading after we copy down. Initially, the size of the cluster is 3 pounds and growing at a rate of 2 pounds per day. So let's translate some things. First off, when we see the word initially, what does that say? Time is 0. So we say, okay, so we're told P of 0, the size of the cluster is 3 pounds. and growing at a rate of 2 pounds per day. What does that become? So, and whenever we see the word rate, rate means derivative. Something's changing. That's a derivative. P prime is 0 equals 2. All right. At a later point, the size of the cluster is 6 pounds. Okay, so we don't know what that point is. We'll give it a name. I don't know, T1. 6 pounds. And is growing at a rate of 3 pounds per day. So we basically are capturing 2 moments in time with this thing of mushrooms. Okay. Cool. And now, what are we asked to do? At what point in time, and they emphasize the word time, so our answer better be a time, will the cluster grow at its maximum possible rate? Okay, so what's the fastest that the cluster, or sorry, not what's the fastest, when will it be growing as fast as possible? Oh, interesting, good questions. Okay, so now let's start delving in. We know we're a logistic model. When we're dealing with a problem in logistic model, we tend to want to solve for 2 things, K and M. Now, one of these has a reasonable interpretation, and that's the M. And you should know what M stands for. So what does M capture? What information is being captured by M? The carrying capacity. Also, the long-term behavior. So what happens in the long run? So if you see something like there was a stable amount, or in the long run, or eventually, like cluing you in that, this is the part where it should head towards. That's M. K is a little bit less obvious. It's some sort of rate. Now, unfortunately, we don't have any information about what's going on in the long run, so we can't do that. But we do have our differential equation, and so we can plug these in. So, for example, we can say, okay, we have, plugging in our first P and P prime, we could say that 2 is equal to K times 3 times M minus 3. And then plugging in our second pair, we could say, well, 3, that's K times 6 times M minus 6. So we can put that information in. All right, now with that information in, well, that's something. And it is something. It's 2 equations, 2 unknowns. All right, what do we do? Yeah, so we're going to solve for K and M. 2 equations, 2 unknowns, solve for K and M. And how do we solve for K and M? We try to cancel. What's a good way to cancel? Let's divide. So this tells us that 2/3. The K's cancel. That's why division works so nice. 1/2 M minus 3 M minus 6. All right. We're nervous about fractions, so what do? We get rid of our fractions. This is an old thing you probably learned way back when, so this will make your middle school algebra teacher proud. It's like, oh, they remember cross multiply. I'm so proud of these kids. All right, so we'll get 4 times M minus 6 is equal to 3 times M minus 3. So this tells us 4M minus 24 equals 3M minus 9. Well, we can subtract the 3M. That leaves us with M. We can add 24. So negative 9 plus 24, 15. Okay, so now we know what M is. M is 15. How do we solve for K? We can plug in. All right, so just pick one equation. Let's say we pick this equation. 2 is equal to K, which we don't know. I don't know why I was looking for it, times 3 times 15 minus 3, which is 12. All right, so what does that say K is? 1 over 18, right? 2 equals 36k. Divide by 36. K equals 1 over 18. All right. Cool. Cool. Let's clean up. So we now have our beautiful differential equation, p prime 1 over 18 times p times 15 minus p. So in the long run, our mushroom will get up to 15 pounds. All right, well that's great. Good to know. But that's not what we want to know. We're not asking for in the long run, when does it get to 15 pounds? Well, we can now solve for p of t. So we can say, hey, you know, p of t, let's go ahead, plug things in. We solved for m, we solved for k, and p naught is 3. So we can say, okay, so that's 15 times 3 over 3 plus 15 minus 3, which is 12, e to the minus k, and so e to the minus 1 over 18, and then times m, which is 15t. So far, so good? I'll go ahead, I see everything has factors of 3 in it. I'll go ahead and divide out by a factor of 3. So the top is 15. Then downstairs we're going to get 1 plus 4. 15 divided by 18. I can write this as 5t over 6. Okay. Now, what are we after? We want to know when the rate of growth is as large as possible. What do we have? We have what the size is at any given time. So, if we want to find when the rate of growth is as large as possible, what would we do? We'd do what?
So we know that at its highest point it'll get up to 15, if I know where m is, so we set it equal to that now.
Well, it'll never get up to 15. Where our question is about the growth. We're trying to maximize the growth. We're trying to maximize the growth rate, right? Right now we just have the size. So how do you maximize the growth rate? Well, the first derivative would give you the growth rate, and how do you maximize that? Second derivative. So what does that mean? That sounds like we have to take the second derivative, right? Well, you can do it that way, but we're going to be smart. We're going to use the power of our minds. It's really cool, really cool. Okay, so here's the power of our minds. Let's come to this differential equation here. And I'm going to plot p versus p prime. Because I can see that p prime depends on p. What does this curve look like? P times 15 minus p. The 1 over 18 does something, but let's talk about p times 15 minus p. What is that? What's the shape? If I said x times 15 minus x, what's the shape? It's a parabola. Where do I intersect? At 0 and at 15. Is the parabola going up or going down? It's going down. So this parabola looks like that. So this is p versus p prime. Think of the picture here. We want to maximize p prime. That's when we're at the tallest point. When does that happen? When does our parabola reach its top point in our picture here? And the 1 is being hidden here, so this is 15, just to be clear. So where am I hitting the peak? Where's my rate of change greatest? 15 over 2. So I will maximize my rate of change when my population is exactly half of its carrying capacity. So I'm in between those two lines, 0 and m. So I'm maximizing rate of change at the halfway. So now I don't have to take any more derivatives. I say, oh, I just have to set 15 over 2. That's when my population is half of the carrying capacity. That's when it's going to be increasing the fastest. Equal to 15 over 1 plus 4 e to the minus 5t over 6. Okay, well now we just have to do some simplifying. Any nice things simplify? 15s cancel. Let's flip both sides. 2 is 1 plus 4 e to the minus 5t over 6. Subtract 1. Divide by 4. 1/4 is e to the minus 5t over 6. We're getting close. Now what? Log. Log of 1/4 is minus 5t over 6. So finally, multiply through. We get t is negative 6 over 5 log of 1/4. And that's the answer. Now, if you want, you can actually rewrite this. This is also the same as 6 over 5 log of 4. Because you can put the negative inside. Moving the negative into the log flips what's inside the log. So that's the other answer. So this one requires a little bit of like, oh, God. That's why I put it on the review. If we put it on the exam, less surprises. But it's fun to think about things, isn't it? Like, wow, we can save ourselves work by thinking. It's true. 4 out of 5 dentists recommend thinking. All right, any questions?
Why would PT equal 6?
Why would it, what? Why would it?
Why wouldn't it just be 6 equals 15 times 3?
Why wouldn't it? I think I'm not following you right.
Top
Right?
right. All the way top right. Yeah. No, makes sense.
I feel like I'm like the bouncing.
When it says 15 times, when you plug all the numbers in, 15 times 3.
Right?
So that PT to the left is 6.
Right, this is our P of t.
Why do you think it's equal to 6?
Why don't we set this equal to 6?
Yeah.
Because that would find not when it's fastest, that would find when did this measurement occur. We're not asking when did this event happen. Because this may not have been when it was growing as fast as possible. So you have to keep track of what it's asking for. If the question had been asked, when did the second measurement occur, then I would set this P equal to 6. But that's not, we don't know if that's the fastest growth rate. In fact, we know it's not the fastest growth rate because you can compute what it is. You plug 15 into both of these equations and you get weird numbers like 225 over a number, 72 or something.
Is there a reason why 1 over 18 doesn't?
Well, so the 1 over 18, it'll just stretch up and down. So 1 over 18 stretches the parabola up or down. So the only thing that matters about the 1 over 18, because I didn't put any scale on the vertical axis, mostly I just care about, I should point to, where am I at? I should point here. I care about whether it's positive or negative. So I just need to know, do I open going down or do I open going up? So the 1 over 18 won't change the fact that the peak happens at the halfway point. And so we were using the picture to figure out where to look.
So what would be different about it if it was like flipped over?
Well, that would be a very weird population problem. We don't talk about those things. All right. Let's move on. Number 8, because I am definitely going to go over, and I apologize. If you need to leave, feel free to leave. But if you want to stay, that's cool too. Okay, so now we're moving into second order differential equations, or really I should say higher order differential equations. So, number 8. Verify that we have two functions, x minus 1 e to the x and e to the minus x, are solutions to 1 minus 2xy double prime plus 2y prime plus 1 plus 2xy equals 0. Okay, whenever a problem says verify, what do? Plug it in. That's the cool thing about verify problems. They're pre-points. You can't get it wrong. All you have to do is plug it in. And if it doesn't work, that just means you made a mistake and you try again. And you just keep trying till it works. Okay, so y1, x minus 1 e to the x. We have to take some derivatives. y1 prime, all right, product rule, derivative of the first, 1 times the second, plus the first times the derivative of the second. Now we can add these together, and if you add those together, you get x e to the x. y1 double prime, well, the first times the derivative of the second, the derivative of the first times the second, plus the first times the derivative of the second, which is x plus 1 e to the x. Okay, so there's our y1. We need to find the first and second derivative, so I just do that here. And then we start plugging in. So we have 1 minus 2x times y1 double prime, x plus 1 e to the x, plus 2 times y prime, x e to the x, plus 1 plus 2x times our original function, x minus 1 e to the x. Okay, now we don't set it equals to 0. We have to check that it equals 0. Well, everything has e to the x, so that's good. So I'm just going to factor that out. So that's e to the x. Now I see 1 minus 2x times x plus 1. What can we do? We can FOIL. So that would be x plus 1 minus 2x squared minus 2x. In the middle term, 2x. In the last term, we have x minus 1 plus 2x squared minus 2x. Okay, so we'll start grouping. For our x squareds, we have minus 2x squared plus 2x squared, which becomes 0. Cool. We also have x minus 2x plus 2x, x minus 2x. So, okay, we have to think a little bit here. X minus 2x is a minus x. X minus 2x is another minus x. And then a 2x. All combined? 0. Well, we know where we're going, right? Plus 1 minus 1 becomes 0. So this becomes e to the x times 0, which is 0. And then we say, aha, verified. Right? You plug it in and check, do you get 0?
On the tank problem, I think the error was that you multiplied the concentration of salt by the volume instead of dividing your salt test. So you said like the concentration divided by the volume instead of multiplying.
Probably something like that, yeah. I'll figure it out. All right. Cool. Now there's only, that's half of it. We have to do y2. Okay. y2. Well, the good news is that's e to the minus x, which is a little bit faster to plug in. Okay, so we're going to get 1 minus 2x times e to the minus x plus 2 times minus e to the minus x plus 1 plus 2x e to the minus x. Again, e to the minus x is common. So we have 1 minus 2x minus 2 plus 1 plus 2x. And when we group, like we did a moment ago, we'll see that the 1, the minus 2, and the 1 all add up and cancel, whereas the minus 2x and the plus 2x add up and cancel, leaving us with e to the minus x times 0, which is 0. Verified. Excuse me. All right, that's part A. I may run out of space here. Part B. Find the solution to the differential equation from A with y of 0 equals 2 and y prime of 0 equals negative 3. Okay. Now A said, hey, we verify that two things are solutions, but they don't satisfy these initial conditions. So how do we use A to get B? What's the idea being used? Yeah, so B is testing you on superposition. Because it says, hey, you have a differential equation which is linear. And so that says if you have solutions, you can take combinations of solutions to make more solutions. Well, I should say it's linear and homogeneous. So you can say, so I can take some constant times the first plus some other constant times the second. Okay, so what do we need? Well, we need to see is there an A and B that work. So we're going to do a few things. First off, we take the derivatives. And here, we can do that pretty quickly. And you might say, how are you doing this so quickly? We already took the derivatives. So I'm just copying what they are. All right. Y of 0. Plugging in 0, we get minus A plus B. And y of 0 should equal 2. Y prime of 0 will get 0 minus b, and that should be negative 3. Okay. What can we do? No. We can solve. See that? One equation, one unknown. That's even better than two equations, two unknowns. Okay, so b is 3. If b is 3, what does that say about a? Well, minus a plus 3 equals 2. So a is 1. So our solution will be our a times 1. So we have x minus 1 e to the x and plus 3 e to the minus x. Okay. So there's part B. Leaving us with a little bit of space, maybe we'll make it, for part C, which is compute the Wronskian. Okay. So we want to find the Wronskian of our two functions, x minus 1 e to the x, e to the minus x. Now, Wronskians, there's just, you need to know the formula. Unfortunately, that's not on the equation sheet. We ran out of space because I know you're like, but there's so many things we don't need. You don't need them now, but you'll want them later. And, all right. So, what do you do? Well, what goes into the Wronskian? It's a 2 by 2 matrix. You have two functions. You copy the functions down in the first row. And then what goes into the second row? Derivatives. And again, we have the derivatives. We already worked them out. So we don't have to rework them. We just recopy. Okay. So, this becomes the two diagonals. So you have x minus 1 e to the x minus e to the minus x. And then subtract x e to the x e to the minus x. I'm almost going to make it. Okay, so the good news is e to the x and e to the minus x is cancel. So the first term becomes minus x plus 1. And then the second term becomes minus x. Or this becomes minus 2x plus 1. All right, so minus 2x plus 1 is our Wronskian. So that's part of our answer, so good. But there's also the use this to determine the interval. The solution is guaranteed to be unique. How do we do that? So what do we not want the Wronskian to do? Like, what's bad for our Wronskian? 0 is bad. We don't want 0. So what are we going to do? Well, if we don't want 0, we say, when does the Wronskian equal 0? So minus 2x plus 1 equals 0 at x equals a half. Right? You can add 2x to both sides, divide by 2. So we have a half. That's our bad point. That means we have two good regions. There's the part below a half, and then there's the part above a half. Now, let's finish reading what this says. Use this to determine the interval. The solution in B is guaranteed to be unique. So in other words, you have this solution right here from part B. When is that solution guaranteed to be unique? In other words, it doesn't like say, after this point, it could have split into 20 different things. Well, which side do we care about? And why do we care about that particular side? Do I care about the side below a half, the side above a half? Do I care about both? Do I care about neither? Which one's the important side? And why? And why is it the one to the left, if that helps you to get started? If it doesn't help you, then forget I said to the left. Oh, no, not both intervals.
Do we care about the left because of the Beyonce songs?
Well, of course, everybody likes the Beyonce song, you know, to the left, to the left. But I don't know how to make it a song in this case. You know, to the left, to the left. Choose the left to make the differential equation guaranteed to be unique. No, see, it doesn't flow. It doesn't flow. So there is something in part B that tells you want it to be the left. So I'll tell you, we care about the left interval. But what is it about part B that says, ooh, the left? That's totally where it's at. That's where all the cool stuff is happening.
Because B uses x equals 0?
Yes, our initial condition is at 0. That says we're starting our curve at time x equals 0. And so we are fine with the function will uniquely extend as long as the Wronskian is not 0. So we'll go all the way up to a half, and then it says, all bets are off at that point. So the thing that happens is that essentially lots of solutions at 1/2 come together and then go back out. So that's why you lose uniqueness. That's why the Wronskian is important. So our answer is negative infinity less than x less than a half. This is uniqueness. So that's the answer to part C. I see lots of hands up.
So then if our conditions were at like 1?
If it had been at 1, then we'd care about the interval on the right. Yeah, so we look at where the initial conditions are. Yes?
Wait, doesn't our Wronskian state that, if it's equal to 0, then only then it's not independent?
So the Wronskian states, so if the Wronskian is 0, the functions are not linearly independent. But what that means is that you get things coming together. That's why you lose uniqueness. Solutions merge, and then they bifurcate again. All right. 9. And if you need to go, feel free to go. Number 9. Find the general form for solutions of y seventh derivative plus 3y fifth derivative minus 4y third derivative equals 0. Okay, so this is a very special type of differential equation. It has all the things we love. It's linear, it has constant coefficients, and throw in homogeneous, and we're just going, yes! This, when you see these three things together, I like to say this is a nice differential equation. And the reason I say it's nice is it's really going to turn into algebra. Algebra. Unlike the rest of the test, right? When we haven't touched algebra at all. But okay, so what happens? When you're in this setting, there's a process. So you have your differential equation, and then you're going to translate that into your characteristic polynomial. And I probably should have spelled characteristic before I tried to put it into the box. Which becomes, you get your roots, and then from your roots you get your solution. So there's this process. And so the nice thing is it's a very nice process. So we start at the top in this case. And keep in mind that you may not necessarily start at the top. You may start at the bottom and have to work back up to the top. So all these things can be reversed. Or we might throw you into the middle. You know, just be ready to go anywhere into this process. So we'll run through the process in this case. All right. So, first step, translate into the characteristic polynomial. What's the characteristic polynomial here? You should be able to read it off. R to the seventh derivative, power 7. 3r to the fifth derivative, power 5. 4r cubed, third derivative, power is 3, equals 0. Okay, so we've gone from differential equation to polynomial. Next step, polynomial to roots. So we have to factor. They weren't nice, they didn't factor for us. Okay, that's all right, r cubed, and then we have our, so I'm just factoring out what's coming, r to the fourth plus 3r squared minus 4 equals 0. Now we're not going to ask you to factor anything that's beyond quadratic. So the only factoring tools you need are for up to quadratic. We're not going to ask you to factor a cubic. Now you're probably saying, but Steve, this is 4th degree. That's definitely not quadratic. But what can you do? Well, you can think of r to the fourth plus 3r squared minus 4 as r squared squared plus 3r squared minus 4. And just temporarily we can come up with like a name, y squared plus 3y minus 4. And then you're like, Does this factor? I ask as though I'm writing down like it will factor. The answer, well, I hope. I need two things that multiply to negative 4 but add to positive 3. How about plus 4 and minus 1? Check. Y squared, good. Minus y plus 4y, good. Minus 4, excellent. So what does that tell us? Well, this is really r cubed. R squared plus 4, that's that y becomes r squared minus 1. And, well, okay. So that's r squared plus 4, r minus 1, r plus 1. Because r squared minus 1 factors. All right, so what are the roots? Well, 0, 0, 0. That's from r cubed, repeated 3 times. R squared plus 4, what are those roots? Plus minus 2i. R minus 1? 1. R plus 1, negative 1. Okay, so now make sure you know rules for roots. So you have to remember all your rules for roots. So first off, let's start with our zeros. So what would the first function, our first solution, corresponding to the root 0 be? It'll just be the function 1. The next one, I can't use 1. I've already used it, so what happens there? You bump it. What about the next one? Bump again. So anytime you have repeated roots, add powers of x.
Unless specified on the exam, can we use t instead of x? Or does it really matter?
On this question, it doesn't matter, but oftentimes they'll say y is a function of x or y is a function of t. It'll specify if it's nervous. All right. Complex roots. Okay. Plus minus 2i. What will that become? In general, if you have alpha plus minus beta I, quick side note, just so you remember, it becomes a pair. It's two roots. It becomes e to the alpha t cosine beta t, solution number 1, e alpha t sine beta t. That's solution number 2. So if you have complex roots, it becomes two solutions. Okay, so in our case, plus minus 2i, well, that says the real part is 0, so the e part goes away, and you get cosine and sine. So cosine, cosine, sine. 1, what is that? It'll be e to the 1t. So, oh, sorry. Why do x's. God. Our discussion about t versus x's threw me off. E to the x and minus 1, e to the negative x. Now, this is not the answer for the solution. These are the functions that make up the solution. So what do you do to get the solution? Put it in general form. You superposition. Add constants. Now, you can use letters of the alphabet. You can do like C1, C2, C3. Just pick a system and go with it. F, e to the x. There we go. So a plus bx plus cx squared plus d cosine 2x, e sine 2x, f e to the x, g e to the negative x. All right. Good. Whew. Any questions on this? Almost surely you're going to see something related to this.
Wouldn't minus 2i also be in like the cosine and sine thing?
Well, the thing is that you shouldn't think of plus 2i as becoming the cosine and the minus 2i as becoming the sine. You should think of them as their roots combined. They become these. So technically, what does 2i give you? So technically, it gives you e to the 2ix, which is cosine 2x plus I sine 2x. So that's what this plus 2i gives you. But the thing is that when you combine that with the minus 2i, you're able to pull it apart. So you pull apart the real and imaginary. So you should think of it as these two roots combined give you these two functions. Not that one gives you one and the other gives you the other. It's just their combination gives you them together.
And does the order matter?
No, order doesn't matter. But oftentimes, you know, if they give it to you as a polynomial, if they're nice, who knows if they're nice? But if they are nice, I would probably go with the order that's in the polynomial. But generally, order doesn't matter. We're pretty good to identify. Yes?
And imaginary roots, come in pairs usually?
They always come in pairs. Yeah, because the kind of differential equations we encounter only have real coefficients. And so whenever you have real coefficients, imaginary roots always have to come in pairs. It's a property of algebra. It's a cool property of algebra. Yes?
So does it matter if you start like a e to the x plus b e to the negative x, you still know what that's
It can be whatever order you like. Yes. Because it's just different ways of describing the same solution. All right, number 10. Another word problem. A spring mass damper system has been set up with a mass m equals 2 and no external forces. Okay, so let's recall, how do spring mass damper systems work? There's a differential equation associated with them that has the form mx double prime cx prime plus kx equals f of t. So m is your mass, c is your damping constant, so the damper trying to slow things down, k is your spring constant, and then f of t, that's your external force. And what we're told is that the mass equals 2 and there's no external forces. So as of right now, we know we have 2x double prime plus cx prime plus kx equals 0. So that's the differential equation. Then we're told, so that's the first sentence. The first sentence tells us that's our setting. Given that the general form of motion for this system is given by this expression, determine the damping constant C and the spring constant K that were used. So in other words, it's like we know how the system is behaving. Let's figure out what the constants are. So instead of, usually it's like, oh, you have the constants, figure out how the system behaves. Now it's like, how does the system behave? Let's figure out the constants. Classic Steve kind of question. Always likes to go backwards. Totally is the Steve thing to do. Okay, so how do we figure this out? Well, let's look at our behavior. The fact that it's lowercase a doesn't mean anything. It's just somebody forgot to push the shift key. So a and b are constants, arbitrary constants. We say, okay, we have this system here. We say, look, these kinds of solutions correspond to very particular types of roots. What kind of roots did we have to have? They were imaginary. Can you be more specific? So the roots of our characteristic polynomial. So there's like the real part plus minus imaginary part I. What's the real part? Well, there's no t, so it's negative a half. What's the imaginary part? The 3 over 2. So the negative 1 over 2, that's from the exponential function. The 3 over 2, that's from the cosine and sine function. So now we know what the roots of our characteristic polynomial look like. Well, let's look at this characteristic polynomial. So we first turn it into the characteristic polynomial, 2r squared plus cr plus k equals 0. How do we find these roots? Is there a formula on the equation sheet that could help us? Or that maybe we know? We can use the quadratic formula. So the roots are going to be negative, the middle term, plus or minus the square root, middle term squared, c squared, minus 4 times the first times the last. So minus 4 times 2 times k, so I'll write this as minus 8k, all over 2 times the first root. 2 times the first coefficient. Yes, quadratic formula, good stuff. We all like it? Now, here's the thing. We can think of this as negative c over 4 plus minus c squared minus 8k under the square root over 4. Where's the real part going to happen? Where's the real part going to come from? This is where we have to get the negative a half. Because this part here, it's either going to be an imaginary, something I, or it's going to be real. So this is where the I stuff has to come from. So this has to be the 3/2 I. All right, can we solve for any of our constants yet? We can solve for C. Yes? You say, aha, ha 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 ha. C over 4 equals a half. So C is 2. Okay. We also have to find K. Well, it's not too bad. What do we have? Well, we know what C is, right? So we can put that in. So C squared is the square root of 4 minus 8k over 4 is plus or minus 3 over 2I. All right. Is it okay if we multiply through by 4? The answer yes. 4 minus 8k under the square root equals plus or minus 6I. Okay, how do we get rid of the square root? We can square. So we square both sides. 4 minus 8k. On the other side, when we square, what comes out? 36? Negative 36. We can add 36. We can add 8k. So we can get that 8k equals 40. So what does that say about k? K is 5. And we're done, because we found C and we found K.
When you were solving for like the I section, did you keep the plus minus 3 halves, plus minus 6, like the plus minus 7? Because you set them equal, so it kind of seems like that sign didn't go.
Yeah, we probably could have done that. But the good thing is, once we square, life is good. Any other questions? Yes?
What about that like equation, that big one equation like D in it and the W sign, you know that? So I think it's related to a string.
Don't worry about that. Yeah. I know the homework asks you to do stuff which is not differential equations. It's trigonometry. So we test differential equations. So you don't have to worry about trigonometry stuff. All right, 2 questions left. And they're both the same category. So we're in the non-homogeneous part. Now, will there be a non-homogeneous question? Am I allowed to say such things? Yes or no? How about I can say that on every single past exam, that as far back as I can go, there has been a non-homogeneous question. And we probably will expect to continue this tradition as far forward as I anticipate will go in the future. So you should be prepared to do something like one of these last 2 problems. And so let's talk about them. They fall into 2 categories. Now, the first category, I like to call this one nice. Okay, so how do you recognize if something is nice? You say, well, look on the left-hand side. Is it constant coefficient linear? And yes, it is linear, and we have constant coefficients. Look on the right-hand side. And you say, does that look like something that comes as a solution to constant coefficient linear homogeneous? And the answer is yes, it does look like that. So when those 2 are true, so the left is nice, the right is nice, the whole differential equation is nice. What's the technique? So the technique, we're going to do the method of undetermined coefficients. So that's our technique. All right. Now, what is this? Well, it says, okay, so what's really going on here? Take a step back. I apologize. Sometimes I get into teaching mode instead of just doing the problem. If you're annoyed by that, just say, Steve, stop teaching. Do the math. So what's going on here is your solutions have 2 pieces. So the YC, this is the homogeneous part. It's also known as a complementary solution. and the yp is the particular part. And so solving the homogeneous part is something we should be comfortable with. It's the kind of thing we did a few problems back. It's getting the particular part that's the challenge. So we're looking for a particular solution. And so what happens in the method of undetermined coefficients, when everything is nice, when the stars align, then what we can do is say, oh, we can guess what yp looks like, and then we just have to fiddle with it to make it be exactly the right thing. And what we have to fiddle with are coefficients. So okay, let's go through the procedure. If you encounter such a problem, step number 1 is solve for yc. All right, should I keep track of what our steps are? Step 1, solve for yc. Okay, so yc says make the right-hand side 0. Y double prime plus 3y prime minus 4y equals 0. Find your characteristic polynomial. You factor. And so the characteristic polynomial, that's r squared plus 3r minus 4 equals 0. It factors as r plus 4r minus 1 with the roots of negative 4 and positive 1, which means that our yc looks like a e to the minus 4x plus b e to the x. Now this is definitively going to be x's because these are x's showing up on the right hand side. Okay, so that's step 1. After you finish step 1, you go on to step 2. Now, step 2 is we're going to find yp up to coefficients. So in other words, we're not going to get exactly yp, but we're going to get close. So how does this work? So this is the method of undetermined coefficients. I like to think of this as you're making a list. You know, as the song goes, you're making a list, checking it twice. You're going to find out which functions are nice. Okay, so how does one make a list? Step 1, you look at the function on the right-hand side. You say, okay, look at the pieces. What pieces do you have? Ignore the coefficients. The coefficients don't matter, just the functions. How many parts do we have? 2. You got e to the x, and you have x. Okay, so we're making our list. You grab the pieces in the list. All right, and then there's 3 things to check for. You ask question number 1, do I see any powers of x? Well, do we see any powers of x? Not x upstairs like e to the x, but x downstairs. And yeah, there is an x downstairs. If there's a power of x downstairs, what do you need to do? All the powers of x that are less than that. Essentially what's happening is what you're seeing is that there's a repeated root. So that's how you get a power of x. Then you have to get all the lower roots as well. Okay, so that's step 1. Step 2, you say, okay, do I see sines or cosines? Because they always like to hang out with each other. They're like BFFs. No sines, cosines here. Of course, who knows what problem you'll see. Now, step 3 is the one that you got to be careful of. You say, well, does anything on my list overlap with functions from YC? Yeah, we have overlap. When you see overlap, what do you need to do? Bump it up. Bump it up. Bump it up. No, sorry, I don't have any rhythm. Okay, so we end up with 3 pieces on our list. Well, what does that tell us? It tells us that yp is going to look like some constant times the first function, some constant times the second function, and then some constant times the third function. Now that's not yp yet, but that's what yp will look like. Right? So this step says find it up to coefficients. So now we have to find the coefficients. So that's our next step. Okay, so we'll call this step 3. Solve for your coefficients. And you'll notice the name of this method is method of undetermined coefficients. when it talks about method of undetermined coefficients, these are the undetermined coefficients. It says you solve for your particular function up to these undetermined coefficients, and then you have to determine them. So how does one determine these undetermined coefficients? You plug it in. Because what is it? It's a solution. And if you have a solution, run the verify idea. Run it through the machinery. Okay, so we're going to take yp double prime plus 3yp prime minus 4yp, set that equal to 10, e to the x minus 16x. So we have to take derivatives. Are you trusting of me right now? Can I go ahead and take the second derivative and you're like, yes, yes, I believe you. Okay, good, good, good. So, when you take the second derivative of x e to the x, you're going to get x plus 2 e to the x. You do the product rule, clean it up, do the product rule, clean it up. That's what it becomes. Second derivative of x, 0. Second derivative of constant, 0. Plus 3. First derivative. Whoops, I forgot my constant c. Don't forget that constant c. You'll need it. First derivative. Well, that's going to be cx plus 1 e to the x. First derivative of x will leave us with 1, so we get d. And derivative of e is 0. Minus 4 cx e to the x plus dx plus e. All that equals 10 e to the x minus 16x. All right. Now we go into our hunter-gatherer mode. We're going to be hunting and gathering coefficients of our functions. So we see a couple of functions here. For example, we see x e to the x. In the first part, there's attached a c. The second part, don't forget the 3 in the front, is a 3c. The last part, minus 4c. We'll clean that up in a second. Plus, we have e to the x. From the first term, we'll have c times 2, so that's 2c. From the second term, we'll have 3 times c times 1, so that's 3c. And then there's not an e to the x in there, so that's good. How about x? Well, there's only one x. It's over here. So that's minus 4d. How about constant terms? Well, there's a 3d and a subtract 4e. Okay, so we haven't changed the left-hand side. We've just rearranged the left-hand side. So we've sort of, if you like, expanded it and then grouped things. Group it by function. Any question on where these coefficients came from?
I have one quick question.
Sure.
Right there where it says in the green minus 4 parentheses, is that c or is that another parenthesis?
That's the constant c, yes. Hard to tell with my handwriting. All right, let's go through these. C plus 3c minus 4c is 0, which is good because we don't want any x e to the x's because there shouldn't be any x e to the x's over there. 2c plus 3c should be, well, it's 5c, but it also should be 10. So you're matching coefficients on the two sides. So that's why we group the functions together and say, let's match the functions up. So 5c, which is the coefficient on the left, has to match 10, which is the coefficient on the right. Minus 4d, what's true about that? That has to match up with minus 16. So minus 4d equals minus 16. What about the 3d minus 4e? Because there's nothing for it to match with. So it's 0. So if something's missing on that side, it's just 0. Okay, so that gives us 3 equations. 5c equals 10, minus 4d equals minus 16, and 3d subtract 4e equals 0. Let's start with the top equation. 5c equals 10. c is 2. Minus 4d is minus 16. d is 4. d is 4. 3 times 4 is 12 equals 4e. e is 3. So our yp is, so put in c is 2, so 2x e to the x plus 4x plus 3. Okay, continuing on our story. So this is a big part. So you want to make sure you understand this step. You found your general form, you plug it in, solve for your particular coefficients. Now we're ready for our next step, our fourth step. All right, general form. So how does general form come about? Well, you have your pieces and you just put it all together. So you say, okay, our general form is a e to the minus 4x plus b e to the x plus 2x e to the x plus 4x plus 3. By the way, we want to know where to stop. So sometimes the problem will say, find the particular solution. If the problem said find the particular solution, you're done here. Sometimes the problem will say find the general form. If the problem says find the general form, you're done here. So this is your yc plus your yp. And then some problems will go one step further and say, oh, I'm not going to give you, I don't want the particular solution, I don't want the general form. I want initial conditions satisfied. So that gives us one more round. Step 5. Solve initial conditions. All right. So what do? Well, we know our y, so we should probably write down our y prime. So we're going to have y prime minus 4a e to the minus 4x plus b e to the x plus 2 e to the x plus 2x e to the x. So I did the product rule here. Plus 4 and plus 0. So there's our y prime. So I had y, I took y prime. Plug in 0. Y of 0. Well, it's a plus b plus 0 plus 0 plus 3. And y of 0 equals 1. Y prime is 0. Well, that's minus 4a plus b plus 2 plus 0 plus 4, so that's plus 6. And then that equals 4. So we have two equations. Our two equations, a plus b equals negative 2, minus 4a plus b equals negative 2. Okay? Yes? No? Now I want to point out here, you cannot solve for these a's and b's before you found y sub p. Y sub p affects these equations. So don't solve for a and b. So don't find, your a and b here early. You have to wait till the end. You have to wait till you have yp in. Okay, two equations, two unknowns. Well, subtract. And what do you end up with if you subtract? A plus 4a is 5a. Minus 2 minus minus 2 is 0. So what is a? 0. What is b? Negative 2. So our final answer Here's our final answer. It's the final answer. Ba-da-da-ba-ba. Okay. So y equals, the e to the negative 4x goes away. That can happen. No worry. So minus 2 e to the x plus 2x e to the x plus 4x plus 3. All right. Good. So be ready. This is the one that we tend to like more often because there's a lot of things that happen. And there's lots of algebra involved here. So that's a huge theme for this test. Lots of algebra involved here. So be patient. All right. Are we? Any questions? If there were sines and cosines, make sure they're in pairs, and then just add it to your list of here. Yeah. So I think there might be a quiz problem that involves sines and cosines. Maybe? Does no one do the quiz problems anymore? They're pretty good.
For the first particular solution, you always just add a constant. So, yeah.
Well, you add a constant because it's on your list. So this is like e times 1. So if your list had just been x e to the x, then your only particular solution would be cx e to the x. So you add a constant here on the end. That plus e reflects the fact that 1's on your list. Not that you always add it.
How did you get x e to the x as being
So we had e to the x initially from here. So e to the x was our initial list. But then we had to clean it up. Now the problem is that e to the x shows up in our homogeneous solution. So if you plugged e to the x into the differential equation, it would vanish because it's a solution. We say, well, that's no good. We don't want it to vanish. So we say, oh, well, if you don't want it to vanish, just bump it up. So that's why you do it the x. So essentially the goal is no overlap with the homogeneous solution because anything in the homogeneous solution vanishes and it's not useful. So that's why you do it. Okay, all right, you've been super patient and I am so sorry for going so long. I hope this is helpful. Let's finish it. Let's do it. Okay, the last one. So given that y equals ax plus bx squared is the general form for solutions of x squared y double prime minus 2xy prime plus 2y equals 0, then find the general form for solutions of x squared y double prime minus 2xy prime plus 2y equals 2x squared log x. Okay, cool. Now, this falls into a very specific category. If you see second order, you see linear. So here you have y double prime, y prime, y. That's what we mean by linear. Non-homogeneous. And not nice. Now, you can be not nice in two different ways. One way to be not nice is the coefficients over on the left are not constant. The other way to be not nice is if the function doesn't look like something that comes out of a constant coefficient linear homogeneous differential equation. Here it's, we get a 2 for 2. So this is really bad. This is very not nice. So when you see all of these things, you're like, okay, I know exactly what this is. This is variation of parameters. There's no doubt. That's the only tool you have. Now, I will say that for many problems that involve method of undetermined coefficients, variation of parameters works. Do not go that way. Variation of parameters is like last ditch if you must use it. If you can use method of undetermined coefficients, do it. Your life will be so much happier. Your points will be so much higher. So, all right, so how does variation of parameters work? Well, the answer is you grab your formula sheet, you grab and you say, hey, there's this nifty formula that says y equals minus y1 integral y2f over Wronskian y1 y2 dx plus y2 integral y1f over Wronskian y1, y2 dx. And once you know its variation parameters, you grab the formula and you say, I'm just running through the formula. I'm totally mindless at this point. All I have to do is make sure I understand what's y1, what's y2, what's f. So let's talk about y1 and y2. y1, y2, when we're looking for y1, y2, these are solutions to the homogeneous differential equation. All right. So, do we have solutions to the homogeneous? In other words, replace the 2x squared log x by 0. Well, that's the homogeneous differential equation. So, are there solutions? There are solutions. So, we have x and x squared are our solutions. So, these are our y1 and y2. So, they're either going to be easy to derive or they're given to you. Okay? So, that's y1, y2. What's our f? Well, our f, you have to be a little bit paying attention. So the general form for these is you have y double prime plus something y prime plus something y equals function f of x. So this is your f. So you're tempted to say it's 2x squared log x, but that's not true. It's not 2x squared log x. Why is it not 2x squared log x? What do you need in front of y double prime? You need a 1. That's not a 1. That's x squared. So we're going to make it 1. How do you make it 1? Cool technology called divide. So divide everything by x squared. Y double prime minus 2 over x y prime plus 2 over x squared y equals 2 log x. Okay? So there's our f. Our pieces are now in play. We have all of them down. We just have to work through. wy1, y2, what does that refer to? The Wronskian. So this is a great way if we want to test you on the Wronskian. So we've mentioned Wronskian before. Write the functions down. Write the derivatives of the functions down. Go down the diagonal, 2x squared, subtract up the diagonal, subtract x squared. So our Wronskian is x squared. So here we go. Now, once you have your pieces, just put it in. Don't even think hard. Just put them in. So we have minus y1, so that's minus x integral. y2 is x squared times 2 natural log x. Divide by the Wronskian, which is x squared. dx, we'll work through that integral in a second, plus the second integral, and that's x squared, that's our y2, integral, y1 is x, 2 natural log of x, divide by x squared dx. So I know its variation of parameters. I have my formula. I know what my pieces are. I identify y1, y2, f. I'm plugging it into the formula. That's up to this stage. Everything after this is running through the computations. Clean things up, and hopefully we have nice integrals. 2 natural log of x. And then over here we get x squared integral 2 natural log of x over x dx. Now, if you want, we can do these slowly, because technically we do have integration by parts on the formula sheet, but I kind of already gave it away. We're not doing integration by parts. So do you want to see the whole thing, or do you just trust me? Oh, you fools! Ha ha! Okay, all right. No, you're not fools. You came here. You're brilliant. Minus 2x. The integral of log x is, as we all know, x log x minus x. And, okay, I'm not going to worry about the plus c right now. Then we have x squared. This integral is actually one we did today. I don't know if you remember it, but it's the natural log of x squared. Because you let u equal log x, then you get 1 over x dx is du. So it's like 2u du. Okay, so we have minus 2x squared log of x plus 2x squared plus x squared log of x squared. Now, this is not the general form, but what is it? It's a particular solution. So if you choose your constants to be 0, it's a particular solution. So how do you find your general form? Well, this is our yp, and they gave us for free. We didn't have to work for it. yc. They just handed it to us. It's amazing. So we put them together. So we have ax plus bx squared minus 2x squared log of x plus 2x squared plus x squared log of x squared. That's a perfectly good answer. And yet, I make it sound like I want to do one more thing. I want to do one more thing to this answer. Can you see anything I can do to this answer? Anything at all, besides the box? Is there anything at all? Sorry, what? We could, but I don't think that's the helpful thing. Is there something we can do to this answer? Is there anything at all that's sort of like, there's something suspicious here? Is there anything we can do? Is there any little simplification that exists that might happen? Doesn't have to. You'd get full points if you stopped here. But is there anything we could do? Is there? What's this? It's a constant. What's this? It's another constant attached to x squared. Because it's an arbitrary constant, you can absorb, this too can be absorbed into that b. So if you go to like Wolfram alpha or something and check your answer, it probably won't have that 2x squared as separate. So that's one more thing you could do. You don't have to. All right, wow, what a problem. Okay.